The sun produces energy through nuclear fusion, where tiny atoms are forced together. When they join, they release a huge amount of energy. This is connected to Einstein's famous equation, E or mc2. This means a tiny amount of mass can become enormous energy because it's multiplied by the speed of light squared. In fusion, when atoms join, a tiny amount of mass disappears, becoming energy. In the early 1900s, scientists realized this is how stars shine. Then in 1934, physicist Mark Oliphant and his team demonstrated fusion reactions in the laboratory. That raised a huge question. Could humans create the sun's power here on Earth? The most common fusion experiment uses two special forms of hydrogen, deuterium and tritium. Unlike normal hydrogen, which has one proton, deuterium has a proton and a neutron. Deuterium is naturally found in seawater, meaning we have a very large supply of it. Tritium, another form of hydrogen, is radioactive and much rarer. When heated, deuterium and tritium fuse, forming helium and releasing huge amounts of energy. But there's a major problem. The fuel must reach over 100 million degrees Celsius. At that temperature, it becomes plasma, which can't be held in a normal container. So scientists use powerful magnets to keep it floating inside special machines. Another method uses powerful lasers to crush tiny fuel capsules. For decades, scientists could create fusion, but experiments usually needed more energy than they produced. Then in 2022, researchers at the National Ignition Facility achieved a major breakthrough. The fusion fuel produced more energy than the laser energy that reached it. But this doesn't mean we have a fusion power station. The real test is much harder. A fusion plant must produce enough electricity to power its own systems, and still have plenty left over to send to our homes and cities. And it can't just work for a few seconds. It needs to operate continuously, safely, and reliably. That's when fusion becomes a real energy source. So is fusion dangerous? Fusion involves radiation and radioactive tritium. But unlike fission, there's no runaway chain reaction. If the precise conditions are lost, the reaction simply stops. So how far away are we? Probably still years to decades from large-scale commercial fusion. But if we succeed, the future could look very different. With deuterium from water, fusion could provide truly vast amounts of low-carbon electricity. It could power cities, produce clean hydrogen, desalinate seawater, and replace our dependence on coal, oil, and gas. One day, it may even help power spacecraft for deep space travel. For thousands of years, humans have burned things to create energy. But in the future, we may learn to control the reaction that powers the stars. And when a fusion power station can run continuously, producing more electricity than it uses, that may be the moment humanity enters a new energy age.